Okay, good afternoon, everyone. I'm glad to present the next speaker, who is actually also one of the organizers of this conference. Organizers before speakers, Ernesto Lupercio, from CINVESTAV. Mexico. His talk is from Toric geometry, and thank you.
Thank you so much. It's very nice to be here, of course. So we're going to explain a circle of ideas that enjoy work with Katzarkov, Lee, and Meersseman. We have been exploring tentatively. And of course, this circle of ideas bring together also a little generalization that will not be so explicit. Young in talks tomorrow will make that aspect more explicit. So we'll omit very much that part. Today I am going to just try to make this relaxing part. So we'll start with some number things. So suppose that we are given a sequence of diagonals of numbers. So this is the first diagonal, and then we have to work it out. And then I have a set of diagonals, for example, the one. Diagonal 0, and then the diagonal 1, and so on and so forth. And now I have maybe I'm going to write diagonal even. And clearly, in case you were template, this can possibly be the Hodge diagonals of the right diagonals. They cannot. Because, well, they are not 1, 0, they lack a symmetry that the diagonal and the right variety would have. So, maybe one more, and then I can keep going. I will just stop at least. So we have this diagrams in our puzzles, we learn to understand what's going on. And of course, every individual diagrams after enough perseverance can be computed. We have a mathematical problem. Then we get this, then we get this, then we get this. We want to understand what's going on. And probably all of you follow the pattern that we can see here. well, it's a very level, but let me just think of a little window, a little diamond window, just like this size, just like 2 by 2. And let me just place it anywhere. Here. And then 12, 14, 18, 18. And I could place it as well. Remove the window. And then let's do it once again. Perhaps remove the columns. Of course, this is the part we immediately notice when we attend this number collaborating. So what we immediately notice is that when we move this little window about the diamonds, we get the next diamond. But clearly, I told you the recursive relation. So, what is going on is that just like classically, and it's beautiful the works of Pascal when he says, well, because really this one is not all that. But again, you know, you move this window. Now the window looks like this. You know, when you move it, this is nothing, you get 1, 1, again you get 1, 1, and you move the window, and you get like this, and so on and so forth. You get Pascal's triangle. Just by moving this window in the generating seed, that is just the number 1 placed on the plate. Here, by moving this double window, what you get is some sort of Pascal's theorem. For this is the generating seed, and by moving this window, I obtain the successive diagonals. So, they are not, they can be the Hodge diagonals of algebraic varieties or K manifolds. They cannot be that. But still, they can be the Hodge diagonals of complex numbers. Why not? They still satisfy the duality, although they do not satisfy that the combination sense. So, and indeed, the way these numbers were obtained is this is the diamond associated to some complex manifold, but this cannot be K. Then this is some complex manifold, and then this is some complex manifold, and then this is some complex. And if you add the basic numbers, you can convince yourself that these manifolds look pretty much like this. If you're more in the C-infinity category, because if you're more people, they look very much like these. Like this. So this is a string and then a lot of ones. And this has the right vertical numbers. These complex manifolds are diffeomorphic to those, are topologically are these, but they have interesting complex structures. So it is this family X0 is, and we call it H, is a Hopf surface. I will say what this is in a minute. And of course, topologically, this is just spherical as well. And this is the Hodge diagram of the concept, the speed. And then all the other ones can be pretty interesting, very mysterious complex structures. All these other manifolds, all of them are non-commutative, scalar, complex manifolds, and they have this recursive nature to the diamonds, and this is very interesting and very possible because it is not the case at all that this is not the case. Except one is not an analytic vibration of an example. It's a completely different complex structure. What it is far more interesting. So, but you cannot find topologically this would look like this, and topologically is okay. Topologically, this is okay. But not as complex. So these are beautiful, mysterious complex variables. Nevertheless, they are secretly related. What is secret? What is going on? Why are they related? And where it is going to take us? How come this seems to talk to all of them and generate all the possibilities a la Pascal in 2 dimensions? So this is the mystery that I would like to. That this is the case though is our first theory. So that's the case with evolution with manifolds, and this is happening. And later the lesson. So, just as the argument. No. So, but this is not what is going on. As far as the Betty numbers go, this is enough to prove the Betty number approximately, but not the Hodge number. So, that's a mystery at hand. Well, what can you do? You do the obvious thing. Rather than write numbers, you write the generating series or generating polynomials, you write the generating polynomials. In each case, for example, if I want to go from here to here, then I like to understand this little window thingy in a different way. So, well, I write a polynomial 1 plus 2a plus x squared plus 3y plus 6y plus 4x plus y plus 2x plus y plus 4y plus 3y squared plus 6x squared plus. Well, I'm not going to write it all unfortunately because lack of language. And I divide over, well, just this thing here. So, if I want to understand the recursive relation, I'm going to generating polynomials. This is what one does. And then I divide one polynomial by the other polynomial and not. And indeed, I immediately see that this is what I would have expected from the topology definition. I get 1 plus x, 1 plus y. That is, it is the polynomial associated to the Hodge diamond of C star plus C star of this topology. So, this is 1 plus x plus x y. 1 plus x y. 1 plus x y. And this is the polynomial associated with the cosine of curve. So somehow this little window thing is the act of multiplying by this polynomial that I would call the polynomial of an elliptic curve. And here I will have a polynomial x1, the generating polynomial is polynomial. Well, I have a polynomial, and then one can prove in this here, part of the first one, of A, this is A is true, the polynomial, the cosine of for these complex variables. That is the family of Katzarkov manifolds. There are manifolds that have interesting complex structures. Very interesting. They are complex manifolds, they are non-catered, non-symplectic, non-algebraic complex. But of course, now what I am saying is that P of x and 1 is the polynomial of x times the polynomial of the and this is part B of the zero. This is part A of here. So you start thinking numbers, and these are an elaborate combinatorial calculation. In cohomology, what do I have to do? I have to compute for all these manifolds HP, HQ, XL, omega P, like this. I have to compute that sheet of homology to compute, and then I have to remain in the terms. Do it all in the result. And then I know this, I do this for computation of this polynomial. I know this is, I can do this very large. And in fact, this implies the following formula. The first one is if you like that kind of thing. So if you like that kind of thing, the formula is I've had some range. I think this. But I want to now that I know the other Katzarkov and the I want to switch notation dramatically and call it HN. Where H0 is just the copy. Well, A copy. Interesting complements. So, part C of the theorem is Hn is m minus 1 p minus 2 m q minus 1 plus m minus 1 p m q. So these are the function numbers of this Katzarkov was the theorem. And that, if you want, B is just the statement that E of Hn, the polynomial of Hn, is 1 plus x to the n minus 1 plus y to the n, 1 plus x squared y. That's a beautiful formula for this. Now, when I get the Hodge numbers and the Hodge variables, I get the Hodge numbers and the Hodge variables, and I assemble them in a polynomial like this. This is called the Hodge characteristic. It's called like that, the Hodge characteristic, and in this case it was P of x. So it's called the Hodge characteristic. So the Hodge characteristic of xn is this beautiful problem. That's the thing. I only need to compute the first one because I know now the recursive image is not very clear. So this is the Hodge characteristic of these mysterious complex. There it is. But I like to understand why one is talking to the other. What's going on? Why? So I remind you now that we want the document for what the complex structure of manifold is commutative problem. So well, so essentially, I'm going to do a little bit more general, in fact, just to save a little bit of time. And I'm going to consider the Calabi elements. Calabi. And they will also be what I Calabi. They will also be complex manifolds that are not only non-complex, okay, interesting. But now they will not be of that. Although it's the same, that's why we're going to take two copies of that in a way. So I take Cn minus 0, Cn minus 0, and then I add. On a point here by a complex number like this. Formulation can already see that well, it's into coordinates, you know. I could do it on only one coordinate and then I would have the coordinate by yourself on location. From this you can immediately see that these give me a diffeomorphism of the Calabi manifolds Mn to the product of these two spheres. If you use only one copy, then you get this S3 with for n equals 2. Mn and then he will get Cp minus 1 cross Cpn minus 1. So, in the particular case of the softness, let me give more examples. So, this is, and they call complex manifolds. Natural. There is no natural complex manifolds. The definition is obvious that they are complex manifolds. But notice that I use the exponential function. Notice that I use the exponential function. And this is the and also notice that I didn't illustrate this. So notice that I use the exponential function and that I didn't use anything else. Okay. So that's the definition of the Calabi and manifolds. And we'll take again the whole manifold. Just taking one copy of that. S3 cross S1. And notice that it's very natural, CP1, S2. And then of course this is an elliptic curve. This is S1, S1. And this is an elliptic curve. It's a purpose. Okay. Notice though that this this whole thing is sort of a complex version of vibration, because the classical topological vibration is like this. Remember that there is one big thing, and there is one big thing. This is indeed topologically, it is the whole vibration times 1. Did the volume disappear or technical difficulties? No, with me.
We can hear you for the moment.
Just for the recording. apparently the battery just collapsed.
It happened before, so.
Yeah. Well, I'll just take this one. So it's like a complex version, complexification of the Hodge vibration, complexification of the Hodge vibration gives you the Hodge surface. That is the simplest story here. So what about the several things, you know, I should say here about the Hodge surface. Where it is, where it is, here it is. So, one, the codiral dimension is minus infinity. This is easy to check. All the plurigeneral vanish. The geometric genus is zero. Of course, pi1 is Z. And is the first example in history of a non-Kähler metric. The first example of non-Kähler. And it's very natural for Hodge to have discovered it because it's just the complexification of the Hodge vibration. But it gives this very beautiful, mysterious, complex structure that is well not algebraic. You need the exponential function to define this complex structure on the either the exponential function or the logarithm. So maybe I should say that this is a log transform. The log transform. And these are also log generalized log transforms. And now, well, can we do this for the Calabi-Ekman? Well, we'll see. But for now, we have this beautiful formula for all the Hodge characteristics, all the Hodge numbers, of all the. But this is only the Hodge. What about the quasi-Hodge? Well, I would have to write more formulas, but again, it gives these subtle complex structures on things like this, where you add 2 copies of the circle at every step just to be on the right, even dimension situation. So you give you add 2 copies of this one, and then it was H0, the Hodge, and this will be H1. And although topologically you're multiplying by real 2-dimensional dollars, the complex structure is something twisted, complicated thing. So these are, nevertheless, we have now this formula for all the Hodge characteristics, for all the quasi-Hodge methods. So the next obvious thing to do is to investigate where this is coming from. And now it is very, very, very natural to consider the concept of a motivic ring because it starts to be motivic. So, but really, motivic rings are only well defined for algebraic. I'll do it now. And I'll explain why it is the relevant restriction. So I'm going on a limb a little bit by saying that we'll be able to understand this phenomena with the help of motivic rings, because the whole point is that these complex manifolds are not algebraic. But here I go, nevertheless. So, So what do I mean? Well, the cheapest version of a Motivic ring is just a K0 bar. So let me try that. The well-known definition. So bar is a category of parameters. And if you want today, we are only working with complex. Although there's more fun to check. Doesn't be very straightforward today. So get K0 bar. And what is K0 bar? Well, if V is a variety, then this will be its isomorphism class of varieties. And of course, this is the more simplest possible way to go about it. With covers, we could do many things, and we should do them at some point or another, but not today. And then I put the famous scissor relations. For y in x is closed. So what am I doing? Well, let me do a couple of examples that are not varieties. And now let me explain how this is pretty hopeless. But let me see. But it is not. So the first thing is that let's just do K0. Well, you can be able to go thing. Or at various stages. Let me do K0 polygons. And in R2, inside R2. Well, then we get formal sums of polygons, isomorphism classes of polygons under the orthogonal group O2. And then I do this polygon minus polygon, well, equals polygon minus polygon, and it's still a polygon. It has to be a map of polygons. Usually. Okay. And here, two things happen. The first is that there is a kind of the situation where you go classes here. Is square parentheses, and then here you can go to the real numbers by area, and of course this produces. If you think about it, the product of polygons is still a polygon, and so this becomes a ring. But of course, I have to go into polytopes. So let me just not think about it. I will have to go into polytopes in any direction to make it into a ring. Then do that. But even this, K0 polytopes, well, has a morphism into R. Well, the addition is the union of polygons, addition is union. And it turns out it's not bad, but it's not entirely trivial. And this is the interesting part. That is an isomorphism. That an area completely determines the scissor class of a polygon. So it's a measure. So such a homomorphism to some abelian group, it's called a measure. And individually, but the proof is interesting. You can get to any high school student, and but even you will discover, I guess, as I said, what you have to do is to find good polygons to get. So these polygons are called rectangles. So you have to cut everything and glue it so that it becomes a rectangle. And then you have this kind of good generators of a rectangle. And this, if you think about it at home, it's exactly a process of quantifier elimination for expressions in inequality. So to transform this thing into something equivalent, but that is just to inequality, inequality like this and this, x less than just like this. If you think about it a little bit at home, is the process of quantifier elimination. And there is various flavors of quantifier elimination, some of them are pretty strong. These ones, very low alcohol, but there is more and more and more. Let me give another example. But the whole thing is that to prove this kind of thing is quantifier elimination. That's the thing, or equivalent to. So that's for polygons. Well, and this justifies that a homomorphism to an abelian group from such K0 ring should be called a measure, a Motivic measure. There's something Motivic about it. Especially when you start changing keys and things. I can say a couple of words about it. Another example, though, is K0. I don't even know what to call it. Zero ring complexes. I don't know. Probably. But let me well, now you can imagine, is topological spaces, homeomorphism class of topological spaces, and now we have this for a closed topological space. And this is really now a ring because now we know how to do the product of single complex. Now it's really a ring. And now you do the thing, and this is MCW. Of course, there's a morphism. We would call this top. And here I start to get fun. And this goes to Z or whatever, I don't know. And this is a ring homomorphism. The Euler characteristic is a ring homomorphism. But of course, it can be factored, this can be categorified or whatever they say these days to K0 of finite dimensional vector spaces. Finite dimensional vector spaces. So that X goes to the obvious one, to the K, HK of X. I don't know, C or Q or whatever. And so you have this finite over Q, finite dimensional vector space over Q. And this category also admits a K0, okay? And this gives you, and then the dimension thing gets you there. And so you can factor this homomorphism through a slightly more categorized version of the number, the Euler characteristic. It's kind of this, with this vector space. But have the dimension of the Euler characteristic. Because subtraction vector space is in K0 is just taking generators, I don't know what to say. No. So you have this ring homomorphism, and the theorem is that this is the homomorphism again. So one may think that these rings are very, very simple. One of those are, the other was set, but for algebraic varieties, this is vastly non-true. This ring is enormous. Logicians have bounds in the cardinality. And here, you can think of this as literally a theorem in linear algebra. You organize the thing, and inclusion-exclusion principle, and pigeonhole principle, and whatnot. Just this story. But it could also be construed as storing quantifier definition to get nice models, nice basic models, so that every space you want to take to this basic model of a space. But here it's very easy. You just put together all the cells of the same dimension, just the cell, the concept of cell gives you, but the concept of cell is a concept where all the cells, or if you want to think it in the mind, cell means all the quantifiers have been eliminated. That's a cell. The same as in the polygons. A cell means all the quantifiers have been eliminated. So now you divide into cells and you know that. So quantifiers have been eliminated again through this. Now it's much harder to eliminate quantifier. Let me just describe a beautiful thing that although we know the proof is extremely trivial. It's very natural. I mean, it's known mathematics. It's a consequence of the results of the theorem. The term on the results of the theorem. Nevertheless, the result blows mind. So you take this ring and you want to know how large it is or whatever, and then you start trying to get measures, and then here you go. Well, again, you go here to set of a letter. Not set, like if I just a number. Here, if I put what I'm going to put here, there would be no hope. And here is, I said, to the summation, the Betti number next to it. Okay. The generating function for the second. And if I try to do that here, no, this is already isomorphic to Z. It won't remember the Betti numbers. It will not remember the Betti numbers. Quantifier definition will not remember the Betti numbers. But there is this theorem here that says that this thing, the Poincare polynomial, Poincare, is a ring homomorphism, and is the universal homomorphism to the polynomial ring in one letter. The biggest homomorphism to the polynomial, and it's all it covers all of the polynomial ring. So this is no longer possible. This cannot be just said. It cannot just be the other. But this is weird. Let me know what this is saying. What this is saying, algebraic. What this is saying is that if I have an algebraic variety, and then I cut it into variety, into semi-algebraic variety, and by some miracle, I glue it into a rather different algebraic variety. I glue the same thing, but I glue a different variety. Then it has not only the same order, which is this one, at the same Betti number. It is so weird. There is a wise word. Now I'm going to give you a new definition of the Betti number that uses no homological algebra. It says, take the universal homomorphism to Z of U from this ring. The coefficients are the Betti numbers. This is a weak definition of the Betti numbers. Think about it. It uses no homological algebra. What it uses though, when it comes down to it, is quantifier language. It's you're copying the fundamental thing is here that kind of like atomic somehow, and already seen without quantifiers. And if they glue, well, they will have the same stuff. But it's a definition that is not homological algebra. And part of the theme of these ideas is that for many statements in mathematics, and of course, one has to prove that this is really the Betti number, and the proof is not easy. If you really would want to write a proof, just ask it all would be a very good. And I will explain the proof. I will explain the proof of this fact in a minute. But the proof is surprisingly big one. And it's because there is these two kind of roles, homological algebra and logics, that takes you to the same entity by extremely different paths. And you could have defined the Betti numbers like this, and then you be responsible to prove that the ones homological ones are this one. This is not the way historically it happened, but it could have happened like this. And it would be a definition of the Betti number, perfectly good definition of the Betti numbers. And you could even compute them, given the equations. And if you give the equations of the variety, you could then compute them algorithmically in the computer. But what you would be doing is only discriminant and this qualifier elimination to be able to divide into the things that you said. So it's a very interesting story. There are these two paths, you know, and I know some logicians, but very provocative. Oh, wrong to use homology, wrong to use homology. Well, what they are saying is a reaction. Uses it, but that it can be done in a rather different way. It's very surprising to me. Coming from culture that I come, it was very surprising to realize that you could do all these things without ever entering into it. So that's very interesting. Very well. So that's that. I still have 10 more minutes here. In fact, this will be a consequence of that. Imagine these pieces, it is rather special. They cannot remember betas, but they remember more. They remember more, you see? The actual thing, I'm cheating there, is that I don't know what to call it. Here again. I don't know what I'm doing. That is a ring combination. A universal ring homomorphism. And here is universally more in one way. Is the biggest one, sure. But also, I could have talked about the actual formula that defines the variety, not the variety. But the symbolic expressions, the equations that define the variety. And then I could say that the formula, a formula in the language plus I mean rather than I could switch for intersections and unions and use I could define a Motivic ring of formulas, and then I would be able to trace most throughout all the fields or things like that. If I use the formula, not the varieties themselves, and it would be even more patent that is about quantifier elimination, finding proofs to things being homomorphisms. It's about quantifier, it's about finding these rectangles that I can move things into a rectangle, and I can move things into a rectangle, and that's this, then I can multiply rectangles easily. And so while but this is a thing, it's a ring homomorphism. Yeah, important thing. For us, for me today. Now, the typical and this implements. I know this will this, everybody will this. I have a little challenge soon. I said I have to succeed. We just approve of that fact. Proving that all the time. It's kind of fun. I can, I'm sure there is. It's just for fun. Anyway, we have this, and this is a ring homomorphism. And the traditional proof of this fact uses these mixed Hodge structures. And what you would say, it's a lot of probability. And uses this Deline's lemma, that fixes morphisms by the linear structure. It's a typical thing. If you know all these mixed Hodge structures, basic language, you should be able to prove that kind of theory. But I'm going to try to offer a different proof. I'm sure it's well known on the expressions. The way I think about it. Because in this different proof is closer to the idea of finding this rectangle than the one that uses mixed Hodge structures. So I will find these rectangles by some quantifier elimination that is finding a normal form for the thing. And then once you have these rectangles, then you can prove all these things. You're checking rectangles. That's the kind of idea that I will pursue to give. So I will not give the classical proof that is everywhere of this fact, but one that I'm sure is implicit in the logic literature. Well, not so much so in the method literature. That is finding quantifier elimination that allows you to find the rectangles, that allows you to check only on rectangles, and then do the same. And why would I want to do that? Because what we claim is that this other kind of proof, and I'm sure this what the problem, allows me to explain. Because now we don't have the mixed Hodge structures, we don't have the non-commutative. But by this finding a kind of argument, I've been able to explain the phenomenon for the Katzarkov manifolds, for the Calabi manifolds, and for everything coming from quantum Toric geometry. So where is the quantum Toric geometry coming into this picture? Let me try to say a couple of words on all that before we start. Well, it's the following. You see, actually, the Hodge surface lives above P1, but actually it lives above many quantum non-commutative P1s, given by a quantum deformation factor. And so you can, this is P0, and so you can start moving this vibration and until you produce a surgery on the space above. So you move far enough, so more general. perhaps more generally easier to imagine. We developed together with Katzarkov, Meersseman, and some parts of this were developed in a different paper by Antoine Bois, still not known. A way to have the super big modular space of Toric varieties. But of course, only the rational points of the modular space are the classical Toric varieties or Toric stacks. Only the rational points. Every irrational point in between, it's a quantum, a non-commutative space, a quantum Toric variety. There's an equivariant compactification of the quantum Torics. So we have an actual Toric variety here, and maybe another actual Toric variety here. But then here we have these quantum Toric varieties that are equivariant compactifications of the quantum Torics. And so here, well, many things. So for every Toric variety, just like for P1, you have H, and for PM cross PM, you have Calabi-Ekman. For every Toric variety, you have something which we call N, that is called an LBM manifolds. It's a complex manifold, non-Kähler, non-symplectic, non-algebraic, and it lies about every Toric variety. And indeed every quantum Toric variety. And as you move in the modular space, you do surgeries on this manifold. This manifold is no longer a product of spheres. It could be complicated combinatorial connected sums of spheres and topologies of things, very complicated. But they have a complete set. And as you move, you do surgeries here. And well, this is a non-algebraic version of the minimal model problem for Toric varieties. The non-algebraic version of the minimal model problem with Toric varieties. So you can travel in the modular space, and then you start doing these surgeries in these things. And this has been a model now, even with the quantum versions. The quantum versions are quantum integrals. They're probably a quantum integral with operator algebras in Hilbert space. And algebras over there. But they have a moment map, of course. And as you do this, well, you also do operations on the polytopes, and you move and you do these kind of things, you know, you recognize some Toric geometry. And the way this modular space works provides enough information for a problem. This I think we can do it. It's a work in progress to prove this in a particular collection of complex manifolds that are non-algebraic. It cannot be it has to look like a collection it has to be the form. It has to be a range of manifolds that is larger than algebraic, but not too big. But more on that next slide.